Today, I'd like to introduce our topic for STAT 512 final project assignment. The project was made by the group number 12. The team members of that group are Andy Joe Baker, Vader Santos Heringer, and Adar Amagildiev. The topic that we choose is, can a life expectancy be predicted by some socioeconomic variables? So why don't we start with our introduction and research questions related to our research? At first, a little bit of a background. Each country has a life expectancy measure that represents the average number of years a newborn is expected to live if mortality patterns at the time of birth remains constant. This also reflects the overall mortality pattern across all age groups in a given year, which is 2019, in a specified population. Overall, 107 countries represented, omitting those with insufficient data. Also, hospital density in our research is measured in available beds per 1,000 people, including inpatient beds available in public, private, general, and specialized hospitals and rehabilitation centers. Throughout the research, we concluded that the following tools should take place in our consideration. HDI index, aka Human Development Index, is a metric compiled by the United Nations, used to quantify a country's average achievement in three basic dimensions of human development, which are a long and healthy life, knowledge, and a decent standard of living. Released annually since 1990, it can be divided into high if HDI is bigger than 0.8, medium if HDI is bigger than 0.5, and low if HDI is less than or equal to 0.5. We used high as a baseline because our interprets alphabetically. Crime rate is calculated by dividing the total number of reported crimes of any kind by the total population. Undernourished and obese divided by 100K were combined to serve as a proxy for individuals that are not healthy. Our general research question: can a life expectancy be predicted by some socioeconomic variables? For variables, we use beta 1 as a linear impact of hospital density, beta 2 linear impact of crime rate, beta 3 linear impact of undernourished and obese, beta 4 linear impact of HDI class, and as beta 5 interaction between HDI and hospital density. Are three specific research questions that will help us further investigate the potential prediction of life expectancy of the above mentioned variables and their corresponding point estimates. Research question number 1, does the hospital density have an impact on life expectancy? And hypothesis test as written below. Research question number 2, does a crime rate have an impact on life expectancy? And hypothesis test as written below. And research question number 3, do hospitals in more developed countries have a smaller impact on life expectancy? And hypothesis test as written below. We used three main websites to gather all our data regarding to this project. And you can see those websites on the screen. Next, we switch to preliminary testing on data. Our five main assumptions are normality, constant variance, linear relations between X and Y, no outliers. Additionally, we checked for the independency of variables in the design. To check for linear effect of each variable, we first regressed the Y against each of the predictors, and the results were significant. And the model shown on the left had a significant p-value and adjusted R-square of 0.521. We also did the added variable plots that show some outliers and that some variables may have significant added value. For our normality of residuals check, we concluded that residuals in our data are not normally distributed. You can see from the normal plot and significant p-value of the Shapiro test, which is sensitive to outliers. For our constant variance check, we concluded that residuals variance is not constant since the Brown-Forsyth test was significant, and that may be because there was a few outliers in the data. The residuals versus fitted values shows how the variance varies. From now on, Vader will elaborate more on the next steps we took in our research.
Looking at the box plot for each of the continuous predictors, we can see outliers in unhealthy and hospital variables that also seem to have a skewed distribution, while the crime rate has a perfect distribution and no outliers. There were also some outliers in the Y variable. Investigating the outliers further, we did residual plots against the predictors. For the most part, the residuals are evenly distributed, except for the outliers. A series of tests were conducted to search for outliers. First, DF-fits was conducted to look for a case influential on a single fit, and a case was deemed influential if it was bigger than the absolute value of 2 times the root of P over N, which in this case was 0.47. By this metric, several influential cases were found. Secondly, Cook's distance was conducted in search for a case influential on all fitted values. A value larger than the 50th percentile was considered of high influence. Using the F distribution with P and N minus P degrees of freedom, we have that a value larger than 0.913 would have a high influence. And here, no value was close to this, thus there are no high influence points. Calling the influence plot function in R, we have a summary of the largest outliers, and the plot demonstrates higher influence points as larger area. In the first column of the table, we can see the studentized deleted residuals of these points. Using the Bonferroni critical value of 1 minus alpha divided by 2 over n, with n minus 1 minus p degrees of freedom, we have that values with a studentized deleted residual larger than 3.62 are Y outliers. Thus, only case 74 is a Y outlier. A hat matrix value larger than 2 times the average hat was considered an X outlier, and mean hat is defined as P over N. So values with hat matrix larger than 0.131 are X outliers, thus case 51 and 85. Plus, as I mentioned before, there are no large outliers by the Cook's distance metric. Relation between the variables was also checked by plotting each variable against each other to test single relationships, and VIF was conducted to test for possible relationships between a variable and a set of other variables. As no VIF was larger than 10, no multicollinearity issue was present. Due to the failure to meet the normality and constant variance assumption for the residuals, we tried a few different transformations on Y. First, the Box-Cox transformation where using the maximum likelihood methodology, we arrived at a high lambda of 6.5. And after transforming Y, we noticed an improvement in normality as p-value increased. However, the difference in variance across the residuals also increased, with a gap appearing in the residual plot. Thus, we tried another transformation on Y. Using the inverse of Y, we obtained an improvement in the Brown-Forsyth test with a huge increase in the p-value, but the Shapiro test continued significant. We tried other methods such as using the log or the inverse of different X variables, but these methods failed to provide a better result. Because the variance was still not constant in the residuals, we decided to conduct weighted least squares on the transformed data more than once, but it did little to improve the variance and caused the appearance of influential cases on all fitted values, cases 31 and 85. Though we rechecked these variables and they are indeed correct. We still tried the regression without these values, but normality and constant variance were still an issue. Running WLS without these values, we also did not improve the diagnostic. So we chose to use the original data of inverted Y, as these data points are from a class of HDI that has few samples, as will be more discussed later. After all this, we decided to use the regression on the inverted Y, as it was more effective in decreasing non-constancy of variance, and we decided to not use the WLS as it was not effective. We arrived at this model after back transforming. As high HDI was used as baseline, The X4 and X5 variables are dummy variables used to indicate the low and medium classes.
Finishing all of the preliminary testing on our data and choosing our model, we could now move on to testing our research questions that were mentioned earlier. Our first question we proposed was, does hospital density have an impact on life expectancy? To test this, we set up a hypothesis test where our null hypothesis was assuming that there was no impact, which would mean that beta 1 would be equal to 0. The alternative hypothesis was just the opposite to this. From the GLT test, the impact of hospital beds per 1,000 people was found to be significant and thus cannot be dropped from the model. This can also be seen on the output, where the p-value was calculated to be less than the critical value of 0.05. Our second question proposed, does crime rate impact life expectancy? To test this, we set up a hypothesis test where our null hypothesis was assuming that there was no impact, which would mean that beta 2 would be equal to 0, where the alternative hypothesis is just the opposite of this. After running the GLT test, we found that the crime rate variable is significant and cannot be dropped from the model, which can be seen on the output where the p-value calculated is found to be less than the critical value of 0.05. Our last question proposed was, are hospitals more efficient in extending life expectancy in more developed countries? For this test, we made our null hypothesis where it was assuming that developed countries are not more efficient, which would mean that beta 5 would be equal to 0. And our alternative hypothesis was just the opposite. After running the test, we found that the interaction term can be dropped from the model and is not significant, which can be seen on the output where the p-value calculated was found to be greater than the critical value of 0.05. Next, we decided to use the best subset function. And when we did this, we actually got an error with R and it crashed. So we had to take out the HDI.class variable, which is our categorical variable, which means that only continuous variables were left in the model. After doing this, it was found based on the press values that model 2 or 3 are probably the better options. Next, we did the k-fold cross-validation. This output shows the difference between a model without the interaction versus the model with the interaction. And because the model with the interaction term produced a lower MSE and a higher R-squared, the interaction term was maintained and kept in the model, despite the conclusion we found in research question 3. This slide gives a summary of our predictions that we found for each of our beta variables. Something interesting to note on this table is the large confidence interval for the low HDI class. And you can see that beside the description of impact of low HDI on the intercept compared to high HDI. You can see that this is a very large interval compared to the others. And we would assume that this has to do with the low sample size of countries with a low HDI class. There are a few limitations with our model and our testing. Number one is the low precision for countries with a low HDI class. There were actually only 5 countries with low HDI left in the data set, as we had to remove the others because they had insufficient data. This low sample size led to the conclusion we found in research question 3, and with more countries included in the data with a low HDI class, this could change the results we found. It's also important to note that results are reliant on the quality of data collection and could always differ if the data that we found from our resources is slightly inaccurate. Another limitation that we wanted to mention is that because the residuals were found not to have constant variance, this could cause the estimates for the betas to be imprecise. So just a summary from research question 1, we found that hospital density does have an impact on life expectancy, and we found a similar outcome on research question 2 with crime rate having an impact. Research question 3, we found that hospitals in more developed countries are not more efficient in extending life expectancy and are assumed to be the same as those in less developed. So going forward, we would collect more data and see if adding countries with a low HDI level would change any of the outcome.